Alright, our first example of an optical system is relatively simple. Basically what we do is we put two lenses together right after one another. Okay, they're just closely packed together. Lens 1, lens 2. For simplicity, let's say lens 1 is a positive lens, okay, with it's just, convergent lens. Lens 2, I don't know what it is, can be convergent or divergent. What I want to know is you put them together act as a single piece of lens. What's going to happen to the focal point? Is this a combination of convergent lens or divergent lens? And where is the focal point? Okay, that's what I want to know. Now, imagine you do an experiment with this combined lens. Okay, put these two lenses together. You draw a beam parallel to the optical axis. Eventually, it's going to end up somewhere on the optical axis, and that distance is the final focal length. Alright? Is the final focal length. So how do we find the final focal length? Suppose I know f1 and f2 for both lenses separately. How do I find the combined focal length? Well, the idea is we're going to deal with the first lens first, find the image formed by the first lens, and then use that image as the object for the second lens, and so we can locate the final image. Okay, now, I have a beam parallel to the optical axis, so P is infinity. P1 is infinity. I'm dealing with the first lens first. Okay, P1 is infinity. 1 over P1 plus 1 over Q1 equals 1 over F1. Right? P1 is infinity, and therefore Q1 is F1. Alright? Q1 is F1. So Q1 is F1 between here and there. That's Q1. Q1 is F1. That's it. The first image is formed here. Now, look at the second lens. Now forget about the first lens, okay? Forget about the first lens now. The first lens, all it did was it produces a beam like this, another beam like that, and so forth. But you see, these beams would have converged here without a second lens, but the second lens is in their way, right? Is in their way, so these beams cannot really focus at that point anymore. That would be a point behind the second lens. So therefore, this distance would be what? Would carry the location of a virtual object, right? A virtual object. So, using this image formed by the first lens as the object for the second lens, this distance would be a negative value for P2. P2 is negative because it's a virtual object. Therefore, we say P2 is equal to negative negative Q1, which is negative F1, right? Now let's apply the equation for the second lens in order to find its image, which is the final image. Okay, so I have 1 over P2 plus 1 over Q2 equals 1 over F2, right? What's P2? P2 is negative F1. I'm looking for Q2. So 1 over Q2 equals 1 over F2 minus 1 over P2, but P2 is negative F1, so this really is just 1 over F2 plus 1 over F1, and therefore Q2, I can find that out. What's Q2 anyway? Q2 is the distance between the final image and these two lenses. Okay, this is where the parallel beam will eventually end up on the optical axis. By definition, that is the final focal length. So F is really just Q2. Okay, what is that equal to? When you solve that, it's F1 times F2 divided by F1 plus F2. Okay, this is how we find it. You see, we use two things. One is the idea of an optical system. We deal with one image first and use that image as the object for the next guy and so forth. And the other one is the idea of a virtual object. Okay, virtual object. So for for the second lens, the object distance is virtual, is negative because the object is virtual, is behind that lens, behind that second lens. Okay, so here's what we get: F1, F2 times F1 plus F2. Now let's see if this makes sense. Okay, let's see if it makes sense. Suppose both lenses are positive. Both lenses are focusing lenses. So here, after the first lens is going to focus here. Now the second lens is going to focus it even further, right? So it's going to bend towards the optical axis even further. So the combined focal length will be shorter than F1 and shorter than F2, right? You know, it just stops the light even faster because both lenses will focus the beam. Is that true? Well, if F1 and F2 are both positive, then you see this combo, F1, F2 divided by F1 plus F2. That combo is shorter than f1 and shorter than f2. Isn't that true? Because f1 times the factor, which is f2 over fn plus 2f2, that factor is of course less than 1, so it's less than f1. And by the same token, it's also less than f2, and therefore f will be shorter than f1 and f2 is positive and shorter. So the lens, the combo, is even more powerful at focusing, at stopping light beams. Okay, now if both lenses are divergent lenses, both are negative, then what happens? Well, then you're going to get, another combined negative lens, which also stops light even faster. Is that true? Well, look, f1 times f2 is positive because both f1 and f2 are negative. But f1 plus f2 is a negative value, right? Because again, both f1 and f2 are negative. So the combo is negative in sign, which makes sense. And what about the magnitude, the absolute value? Well, the absolute value, again, is shorter than f1 and shorter than f2. So you can end up with a focal point that's even closer to the optical center, but it's a divergent lens. Okay, so that again makes sense. Now, what is more interesting is what happens when f1 is positive but f2 is negative. Now you have to be careful. Okay, you have to be careful. You know f1 times f2 is definitely negative, right? Because one is positive, the other is negative. But what about f1 plus f2? Well, let's see. If f1 is shorter than f2, all right, then f1 plus f2 would have been negative. But f1 times f2 is also negative. That means the combo is positive. Okay, so that tells us that if you put two lenses, one divergent, one convergent, but the convergent lens has a shorter focal length than the divergent lens, you can end up overall with a positive f. In other words, overall the effect is a focusing lens. Does that make sense? Well, yes it does, because the shorter the focal length, the more powerful the lens is, right? You see, if the lens doesn't have any focusing effect at all, it's going to focus the beam at infinity, f will be infinity, right? The shorter the f, the focal length, the stronger, the more powerful the lens is. So you have a shorter focal length, positive lens, and longer focal length, negative lens. So you have a stronger positive lens and weaker negative lens. That's why you end up with overall a focusing lens, even though the focal length will be longer than before. Okay, because the negative lens somewhat weakens the positive lens. Now, on the other hand, if you have f2 negative and shorter than f1, then f1 plus f2 would be positive, yet f1 times f2 is still negative. So overall, you get a negative lens because the negative lens this time is more powerful than the positive lens because of its shorter focal length. Okay, so you see, everything makes sense here, and this is our first example of using the idea of lens system and virtual object. Okay, now let's take a look at a more comprehensive example of an optical system. This time we have a lens and a mirror. Here's a positive lens with a focal length of 4 centimeters. Okay, each dot on the optical axis represents a centimeter away from the next dot. And 15 centimeters down, I have another instrument, which is a positive mirror or concave mirror with a focal length of 2 centimeters. Okay, so from here to 2 centimeters. And I place an object 6 centimeters in front of the lens. I want to know where the final image would be if I look at it from this point of view. Okay, first of all, an image will be formed of this object by the first lens. It's going to be somewhere here. And then that image will be reflected from the mirror to form the second image. And that second image then goes through the lens again, will be forming a third image. And that third image is what you can see. Okay, so I'm looking for the location of the third image. Okay, now we can do so by ray tracing. We can also do so by using ray diagrams, by using the lens and mirror equations. So we can do both of them to see if we get the same result. Okay, now first of all, ray tracing. Okay, ray tracing. I'm going to draw the first image produced by the lens of this object. Okay, so I'm going to draw a line that is parallel to the optical axis. You know where that goes, right? It goes through the focal point right here. Okay, and then draw another line passing through the optical center. Okay, passing through the optical center. So that line gets undeflected, keeps on going. So you know they're going to merge at that point. Okay, they're going to merge at that point. That point is the image location of the object formed by the lens. Okay, and so you have our first image right here. Here's the first image. The way I draw it appears to be about 3 centimeters away. 3 centimeters away from the mirror. Okay, now I'm going to draw the image formed by the mirror. Okay, the image formed by the mirror. First of all, okay, the idea again is that I'm using this object, using this image as the object for the mirror. So here is how I draw it. First one, I'm going to draw a line that is parallel to the optical axis. Okay. Parallel to the optical axis. You know where that goes. It's going to go through the focal point right here. Go through the focal point. Okay. And then I'm going to draw another line. This line passes through the focal point. Passes through the focal point like this. And after that, it becomes parallel. Right? It becomes parallel. It's kind of awkward to draw because it's quite big, but you know, you get the idea. It's going to be somewhere here. Okay, it's going to be somewhere here. That is the location of the second image, somewhere here. So this is I1 and this is I2. Okay, it appears that I2 is about 6 centimeters away. This is I2. I2. It's about 6 centimeters away from the vertex of the mirror. Now, this I2 now serves as the object for the lens. You know, the light rays from I2 will then go through the lens. Eventually, you're going to see it. Okay. So how do we find the final image? Well, first of all, I can draw a line from I2 going through the focal point. You know where that goes. It simply becomes parallel. Right? It becomes parallel. Like this, parallel to the optical axis. And then I'm also going to draw a line that passes through the optical center from I2, passing through the optical center, right? So it does this, undeflected. Where is the location of final image? It's somewhere here. Okay, it's somewhere here, and then, you know, it's going to be like this. This is I3. Okay, this is I3. So this is our ray tracing result. You get an inverted image, real inverted, and a distance 1, 2, 3, 4, 5, 6, about 7 centimeters away from O1. Okay, real inverted, enlarged at about 7 centimeters away. Now, what about our calculation? Of course, the drawing that I made may not be all that exact because of, you know, it's really parallel, that sort of thing. But it gives you a rough idea where the image is. If you want an exact result, you have to draw very carefully. All right, now let's do a calculation, shall we? With the calculation, let's first of all find the location of I1. Okay, I1. With I1, I know the object is placed 6 centimeters in front. So you have 1 over P1 equals 1 over P1 plus 1 over Q1 equals 1 over F1. In other words, 1 over 6 plus 1 over Q1 equals 1 over 4. And that tells you that Q1 is 12 centimeters. Okay, now the distance between O1 and V, between the lens and the mirror, I made it 15 centimeters. But Q1 is already 12 centimeters from here to there. That means that leaves 3 centimeters between I1 and the vertex. I1 now serves as the image, as the object for the second instrument, which is the mirror. So that for the second instrument, which is the mirror, the object size, the object distance would be 3 centimeters from here to there. Okay, so I have P2 equals 3 centimeters. Okay. Then I can apply the mirror equation for this guy to locate I2, the image location of the second image produced by the mirror. Okay, so I have 1 over, here's the mirror equation, 1 over P1, 1 over P2 plus 1 over Q2 equals 1 over F2. In other words, 1 over 3 plus 1 over Q2 equals 1 over 2. Okay, what does that tell you about Q2? Q2 should be equal to 6 centimeters. Okay, see the way I draw it? 1, 2, 3, 4, 5, 6. Yes, it's about 6 centimeters. That's Q2. Okay, so far, everything works. Everything matches between the calculation and the drawing. Now, the final image. Okay, the overall distance is what? The overall distance is 15 centimeters. From here to there is 6 centimeters. So that leaves 9 centimeters between here and there, right? And that is that is P3. Okay, it is the object distance for the third image. So P3 equals what? Equals 9 centimeters. Then I have the length equation again. 1 over P3 plus 1 over Q3 equals 1 over F1. It's still the same length with focal length of F1. In other words, 1 over 9 plus 1 over Q3 equals 1 over 4. Or you can do a little calculation of what Q3 should be. Unfortunately it's not an integer, but you can calculate it. It is 36 divided by 5 is about 7.2. So according to our calculation, the final inch should be about 7.2 centimeters behind the first lens. 1, 2, 3, 4, 5, 6, 7. So it should be somewhere here. Okay, somewhere here. Our rough drawing yields there. So we get about like 2 or 3 millimeters of error, but it roughly agrees with the correct answer. And you can also figure out the size of the final image, by the way. The size of the final image. Okay, you go from the first image, right? You multiply by the magnification, you get the second image size. You multiply by another magnification, you get the next image size. And then by another magnification, you can get that image size. Okay? The magnification, as you know, is Q over P. Okay, so you have to multiply 3 times. 1, 2, and 3 to get the relative size of the final image compared with the object. And you can easily do so. You will find that the image, indeed, final image is bigger than the original. So here is an example how we can do either ray tracing or doing calculation to find the location and characteristics of the final image of an object formed by an entire system of objects, not just one piece.